You move your hand from left to right. That's one dimension. You move it forward and backward. That's a second dimension. You move it up and down. That's a third dimension. Three dimensions. Space, the world we live in. And you think you understand what that means, but Richard Feynman would stop you right there. Because what you just described isn't what dimensions are. It's what dimensions look like to you. And there's a difference, a profound difference, between what something is and how it appears. And once you understand what dimensions actually are, the whole universe starts to look different. Here's the thing most people never question. Why three? Why does space have three dimensions and not 2 or 4 or 17? You might say that's just how it is. That's just what we observe. But Feynman would push back. That's not an answer. That's giving up. The question isn't just how many dimensions are there. It's what is a dimension in the first place. What does it mean for space to be dimensional at all? Let me start somewhere simpler. You want to meet someone. You say, let's meet at the coffee shop. But that's not enough information. Which coffee shop? The one on Main Street. Okay, but when? Tomorrow at 3. Now you have enough information. You needed to specify a location in space and a point in time. 3 numbers for space. 1 for time. 4 coordinates total. That's 4-dimensional space-time. But here's what people miss. Those coordinates aren't the dimensions. The coordinates are just labels, just ways of describing positions. The dimensions are something deeper. They're the directions you can move, the independent ways you can change your position. And independent is the key word there. You're standing in a room. You can move left or right. That's one independent direction. You can also move forward or backward. Is that a different direction? Yes, because you can move forward without moving left. The two movements are independent. They don't affect each other. You can change one without changing the other. That's what makes them different dimensions. Now you can also move up or down. And again, you can do this without moving left, right, or forward, backward. It's independent. That's the third dimension. Can you find a fourth? Can you move in some direction that's independent of all 3 of those? No, you can move diagonally, but that's just a combination of the 3 basic directions. There's no fourth independent direction you can move in space. That's what 3-dimensional means. Not that there are 3 directions like north, east, and up, but that there are 3 independent directions. 3 ways to move that don't interfere with each other. 3 numbers you need to specify a position completely. Feynman thought deeply about this, about what it means for dimensions to be independent, and he realized something crucial. Independence is mathematical. It's not about perception. It's about whether changes in one coordinate affect another. In flat space, they don't. You can change your x-coordinate without affecting y or z. The dimensions are orthogonal, perpendicular, completely separate. But here's where it gets interesting. Is time a dimension? You learned it is. Space-time, 4 dimensions, 3 of space and 1 of time. But time feels different. You can move freely in the 3 space dimensions, left, right, forward, back, up, down, any direction you want. But time, you only move forward, always forward, never back, never stopping. How is that a dimension in the same sense? Feynman would tell you time is a dimension because it's an independent direction in space-time. To specify an event where and when something happens, you need 4 numbers, 3 for position in space, 1 for position in time, and those 4 numbers are independent. You can change when something happens without changing where. You can change where without changing when. 4 independent coordinates, 4 dimensions. But time is different in one crucial way. The mathematics treats it differently. In the formula for space-time distance, for the interval between events, time enters with a negative sign. Space coordinates are positive. Time is negative. Or vice versa, depending on convention, but they have opposite signs. This makes space-time geometry different from regular 4-dimensional space. Time isn't just a 4th space dimension. It's something else. A time-like dimension as opposed to a space-like dimension. This matters because it affects what's possible. In space, you can move in any direction. In space-time, you can't. You're constrained by the speed of light. There are regions of space-time you can reach and regions you can't. The geometry is hyperbolic, not Euclidean. That negative sign in the metric changes everything. Now here's a question Feynman loved. Could there be more dimensions? Not metaphorical dimensions, not spiritual dimensions, actual physical dimensions of space, places you could move if you were small enough or had the right technology. And the answer is maybe. We don't know. Physics doesn't require exactly 3 space dimensions. The equations work in any number of dimensions. In fact, some theories suggest there might be extra dimensions, small ones, curled up so tiny we can't see them. Imagine an ant walking on a tightrope. From far away, the rope looks one-dimensional, a line. The ant can only move forward or backward along the rope. But up close, the rope has thickness. The ant could also walk around the circumference. That's a second dimension, a tiny circular dimension that's invisible from a distance. String theory proposes something similar for our universe. Maybe there are extra dimensions, but they're curled up into tiny circles, so small that even atoms can't detect them, smaller than anything we can measure. These dimensions would exist at every point in space. Right here, right now, there might be 6 extra dimensions curled up, so small you'd need energies we can't produce to explore them. Why would nature do this? Why have dimensions we can't see? Feynman would say, don't ask why. Ask if. Does the math work? Do the predictions match experiments? String theory is mathematically consistent only in 10 or 11 dimensions, 9 or 10 of space plus 1 of time. If string theory is right and we don't know if it is, then those extra dimensions must exist, not because nature likes the number 10, but because the math only works that way. But we haven't detected extra dimensions. Every experiment we can do shows 3 space dimensions. Does that mean they're not there? Not necessarily. It means if they exist, they're smaller than we can probe, or they're hidden in some other way. Maybe matter is confined to a 3-dimensional surface embedded in a higher dimensional space, like how drawings on paper are confined to 2 dimensions even though the paper exists in 3-dimensional space. This idea, called brain world, scenario suggests our entire universe might be a 3-dimensional membrane floating in a higher dimensional space. Everything we're made of, all the particles and forces except gravity, would be stuck to this brain, unable to move in the extra dimensions. But gravity, being geometry itself in general relativity, could spread into the extra dimensions. This could explain why gravity is so much weaker than other forces. It's diluted across dimensions we can't access. These are speculations, theoretical possibilities. Feynman would be careful to distinguish between what we know and what we hypothesize. We know space has 3 dimensions that we can move in. We know time is a 4th dimension that's different in character. We don't know if there are more. The question is open. But here's something we do know. The number of dimensions affects how physics works. Forces behave differently in different numbers of dimensions. In 3 dimensions, gravity falls off as 1 over distance squared. Double the distance, gravity becomes 1/4 as strong. This is because gravity spreads over the surface of a sphere, and surface area grows as distance squared. But in 4 space dimensions, gravity would fall off as 1 over distance cubed. In 2 space dimensions, 1 over distance. The number of dimensions directly determines how forces propagate, and it turns out stable orbits are only possible in 3 space dimensions. In 2 or 4 or higher, planetary orbits would either spiral in or fly apart. The fact that we have stable solar systems is evidence that space is 3-dimensional. Similarly, atoms behave differently in different dimensions. The equations of quantum mechanics depend on dimensionality. Electrons orbiting nuclei, the shapes of orbitals, the stability of matter. All of this changes with the number of dimensions. In 2 dimensions, atoms would behave very differently. In 4 dimensions, different again. The chemistry of life, as we know it, requires 3 space dimensions. Does this mean 3 dimensions is special? Or does it just mean we exist in 3 dimensions because that's where life is possible? This is an anthropic argument. We observe 3 dimensions not because 3 is fundamental, but because observers can only exist in 3 dimensions. In universes with different numbers of dimensions, there's nobody to ask the question. Feynman was skeptical of anthropic arguments. He preferred explanations based on physics, not on the requirements for observers. But he also acknowledged we don't yet understand why the universe has the dimensionality it does. It's an input to our theories, not an output. We measure 3 space dimensions and build our theories accordingly. We don't derive 3 from deeper principles. Now let's think about what dimensions really are at the deepest level. You think of space as a container, a stage where physics happens, 3-dimensional emptiness that things move through. But general relativity, change this. Einstein showed that space isn't separate from matter and energy. Space is dynamic. It curves, it bends, it responds to what's in it. In general relativity, dimensions aren't just directions you can move. They're components of a geometric structure. Space-time is a manifold, a mathematical object that at every point looks locally like flat, four-dimensional space-time, but globally can be curved, twisted, even have different topologies in different regions. When you say space-time is four-dimensional, you're saying that near any point, you need four coordinates to specify locations. The manifold is locally four-dimensional. But globally, space-time could have complicated structure. It could fold back on itself. It could have wormholes connecting distant regions. It could even have regions with different effective dimensionality. Feynman worked on quantum gravity, trying to combine quantum mechanics with general relativity. And in quantum gravity, even the dimensionality of space-time becomes uncertain. At the Planck scale, at distances of about 10 to the minus 35 meters, quantum fluctuations in geometry become large. Space and time lose their classical meanings. The notion of a definite number of dimensions might break down. Some approaches to quantum gravity suggest that dimensionality is emergent, that at the deepest level there's no space or time as we know it, just some abstract quantum information or networks of relationships. And from this, space-time with its four dimensions emerges as an approximation, like how temperature emerges from molecular motion. Temperature isn't fundamental. It's a statistical property of many particles. Maybe dimensions are similar, statistical properties of some deeper reality. This is speculative. We don't have a complete theory of quantum gravity. We don't know what happens at the Planck scale. But Feynman's path integral approach to quantum mechanics hints at something strange. In the path integral, you sum over all possible histories, all possible paths a particle could take. When applied to gravity, you sum over all possible space-time geometries, and that includes geometries with different topologies, different structures, possibly even different dimensions. Does this mean particles explore spaces with different numbers of dimensions? In some quantum sense, maybe. The mathematics includes contributions from all sorts of geometries. Most cancel out. The dominant contributions come from something close to classical, four-dimensional space-time, but the others are there in the calculation. Whether they're real or just mathematical artifacts is a question of interpretation. Let's come back to something more concrete. You experience three dimensions. You can visualize three dimensions. Can you visualize four? Not four dimensions of space-time, but four dimensions of space. Four independent directions, all perpendicular to each other. Most people say no. We can't visualize that. Our brains evolved in three dimensions, but Feynman would say that's fine. Visualization isn't understanding. Mathematics is understanding. You can't visualize four space dimensions, but you can work with them mathematically. You can write down coordinates, four numbers. You can define distances. Take the square root of the sum of the squares of the four coordinate differences. You can do geometry, define angles, volumes, shapes. Mathematicians study four-dimensional objects, hypercubes, four-dimensional spheres, polytopes with properties that have no three-dimensional analogs. These objects are perfectly well-defined mathematically, even though we can't picture them. We can study their properties. We can even project them down to three dimensions and visualize the projections, like how a three-dimensional object casts a two-dimensional shadow. In fact, you can do physics in any number of dimensions mathematically. Physicists do this routinely. Sometimes it's easier to solve a problem in an arbitrary number of dimensions and then set the number to 3 at the end. Sometimes patterns emerge that are clearer in higher dimensions. The mathematics doesn't care. It works in 2 dimensions, 3, 4, 100, even non-integer dimensions, using mathematical extensions. There's a famous result in physics called the critical dimension. For string theory to be mathematically consistent, space-time must have a specific number of dimensions. For bosonic string theory, 26. For superstring theory, 10. These aren't arbitrary choices. They come from requiring that the quantum theory doesn't have inconsistencies, called anomalies. The math forces the dimensionality. Does this mean the universe really has 10 dimensions? Only if string theory is the correct description of nature. And we don't know if it is. String theory makes predictions that we can't yet test. The energy scales where strings would behave differently from particles are far beyond what our accelerators can reach. So the theory remains unconfirmed. Beautiful mathematics. Compelling ideas, but not yet proven to describe reality. Feynman himself was skeptical of string theory, at least in his later years. He felt it made too many assumptions without enough connection to experiment. He valued theories that made testable predictions, theories that could be proven wrong. String theory, at least at the time, seemed too flexible, too many possible versions, too hard to test. But he would also say this: if the math leads somewhere interesting, follow it. See where it goes. Maybe extra dimensions exist. Maybe they don't. The way to find out is to make predictions and test them. Look for effects that extra dimensions would produce, deviations in gravity at small scales, new particles from dimension-changing modes, signatures in particle colliders or cosmology. Experiments have looked. They've searched for extra dimensions at particle accelerators. They've tested gravity at sub-millimeter scales. They've looked for signals in the cosmic microwave background. So far, nothing. All results consistent with 3 space dimensions. But absence of evidence isn't evidence of absence. It just means if extra dimensions exist, they're smaller or more hidden than those experiments could detect. So what are dimensions really? They're independent directions, degrees of freedom, ways a system can change. In space, they're directions you can move. In mathematics, they're coordinates you need to specify a state. In physics, they're parameters that affect how forces and particles behave. But more fundamentally, dimensions are structure. They're part of the geometric framework in which physics happens. They're not just background. In general relativity, they're dynamic. They respond to matter and energy. They can curve and stretch and vibrate. They're part of the physical content of the universe, not just a stage it happens on. And we don't fully understand them. We don't know why space has 3 dimensions. We don't know if there are more we can't see. We don't know what happens to dimensionality at the Planck scale. We don't know if dimensions are fundamental or emergent. These are open questions, active areas of research. Feynman would remind you that this is how science works. We don't have all the answers. We probably never will. Each answer raises new questions. Each solution reveals deeper mysteries. The goal isn't to reach final truth. The goal is to keep asking, keep testing, keep learning. You move your hand through space. 3 dimensions, or maybe more. Maybe there are tiny curled up dimensions right here that your hand passes through at every point. Maybe at the smallest scales, space is a quantum foam where dimensions fluctuate. Maybe dimensions themselves emerge from something more fundamental. Or maybe space is just 3-dimensional. Simple, fundamental. And the question of why is one we'll never answer because it's just a brute fact about the universe. We don't know yet, but what we do know is this. Dimensions aren't just directions. They're geometric structure, mathematical degrees of freedom, physical parameters that determine how nature works. And understanding them, really understanding them, means letting go of simple pictures and embracing the mathematics. The universe has dimensions. We live in them, we move through them, and what they really are is still in some ways a mystery, a beautiful mathematical, testable mystery that physicists continue to explore.